opportunity to highlight some issues that could be relevant for the Cairo. Essentially, and so in that regard, the topic of my talk is impact of hydroclimatic extremes on plants, people, and water supply pools. So here, what I will focus on is I'll talk about fate and functions of plants, people, and water supply reservoirs. I will specifically highlight that how studying that will allow us to do a better prediction of hydrologic extremes and hence have a better assessment of water hazards, which is which is one of the main goals of the Cairo. Okay, so let's start with the first example, which is about impact of drought extremes on plants. Many of you must be already aware that drought can lead to carbon starvation, hydraulic failure, or many other kinds of physiological ailments in plants. And that eventually results in either tree mortality or morbidity or reduction in fecundity. Long story short, the drought stress, and which is becoming more intense and frequent, what that has resulted in is now for the timberlands of the national forests in US, the mortality is much higher than the production. So that's the tipping point we have gotten to, where the growth is much smaller than the death that is occurring. Now, why should we be interested in this as a hydrologist? Well, because a lot of studies have already shown, let's say if you denude the forest or change the forest structure, that has direct implications on the stream flow and water yield from those watersheds. Although there is not a lot of agreement on how the stream flow is going to change. So for example, a recent work by Williams talked about how the yield is going to increase if there has been a forest fire, but another work by Goiking and Tarbatin talked about that only in wet systems or systems with less aridity the yield is going to increase, but in very dry systems it's uncertain. They were not able to ascertain clear explanation of why that is happening. But one thing we are sure about is that the alteration of forest and forest structure and tree mortality, all of that is going to affect the stream flow. What that means is if we want to have high fidelity stream flow prediction, we need to also be able to do a good tree mortality prediction. That will be needed. However, the tree mortality prediction is easier said than done. I mean, it's a very difficult problem, and a lot of people have already written about it. Essentially, the idea is different trees, for the same stress, different trees will die at different times. So it's like, let's say, if we, if Mike Tyson comes and then punches me, and obviously I'll be dead. Now, if it punches some of you, maybe not a good example. Let's say some of you may survive. What I mean to say is, depending on who is there, that ends up determining if you survive it or not. Okay. Now, obviously, it's also dependent on forest structure, covariation of the traits, and then biotic agents. Are there pine beetle infestation already in the area, so on and so forth. So all of that ends up determining mortality, and so its prediction, especially using physically based model, remains very challenging. So what we had done a few years back was to approach this problem from a data perspective, and the idea was based on nonlinear dynamics. So let's imagine that you have a natural system which is in equilibrium. So let's say this is our natural system, which is our forest. And every time it gets a stress, and by that I mean stress or absence of stress here is precipitation and temperature. So let's say if it's a wet year, the biomass will increase, the leaf area index will increase. If it's a very dry year, the biomass will decrease. So essentially, the forest is oscillating right here, okay? But as the forest starts getting, sicker or more and more stressed, what it happens is that this well, the energy well, becomes much more flatter, and the system will just move, it reaches a tipping point, and then the system will move to an alternative stable state, which can be a transition from a forested setting to, let's say, even a grassland. So significant change in the forest structure can happen. Now, the question is, how can we track if a system is about to reach the tipping point? A lot of studies have been done in this regard, especially Martin Schaefer has done it. And essentially the idea is, let's say X is the LAI in this case, and then here is X star, which is the long-term mean, delta is the perturbation. And now you can write this in a way that now you can write perturbation Y is equal to alpha times Y in a previous time step plus a noise. All what this is showing you is alpha is e to the power lambda t. So when this value lambda is negative, this value becomes very small, and so y will reduce fast. So if a system is near the tipping point, what happens is lambda is close to 0, so this value is close to 1, which means that yt and yt plus 1 are going to be very autocorrelated. Okay. Now tracking autocorrelation, one will think, okay, we can easily track it, but it can become a bit difficult, especially when the forcing conditions are autocorrelated as well. So now the question is, how do we know LAI is autocorrelated because of the change in resilience of the trees, or because of the changes in the autocorrelation of the meteorological forcing? And that's where it becomes a bit difficult problem. So anyhow, the student who worked on this, Yanlan Liu, what she did was she developed this Bayesian inference-based dynamic linear model. Only thing I will try to highlight here is there is a theta term which is tracking the autocorrelation, and this linear model is able to isolate the influence of meteorological forcings, their autocorrelation structure, and the noise from that of the resilience. So anyhow, when we look at it, what this kind of approach does, it is you can see right here is the NDVI, and there are many time periods when the NDVI is very small, but this is not when this approach will identify is the system going to die or is the forest going to die. Only when the early warning signal, here it starts showing in red, that's when it means that the system is about to die. So this early warning signal is able to identify that the system, the forest is about to die, or trees are about to die in the forest almost 19 months before it actually happens. So this kind of predictive tool can be incorporated in a hydrologic model to, especially in a system which is around the tipping point, to do predictions. And you can see the performance of the model. If we just compare it with the drought index, obviously the mortality area does not correspond to the drought index, but the early warning signal does correspond to that. And we did all kinds of validation for different kind of vegetation types, and also for different time lags. This is the accuracy. So we can see that the R-square accuracy is around or above 0.6, even with 12 months lead time. Okay, so let's move on to the next example, which is about the impact of hydrologic extremes on water supply pools or reservoirs. Now, there has been numerous studies talking about how hurricane leads to floods, or quantifying the devastating consequences of hurricanes. But not a lot of studies have looked into whether hurricanes are actually important or could be important, especially for southeastern U.S. The reason we pose this question is because in southeastern U.S., majority of the reservoirs are actually within ear reservoirs. So it's very different than western U.S., where the reservoirs are over ear systems. What we mean by that is within ear reservoirs are smaller reservoirs and generally only store a fraction of the annual flow coming into the reservoir, which means that the storage in those reservoirs are very sensitive to seasonal variations in flow, or even could be sensitive to daily variations in inflow. So to evaluate it, what we did was something which most of us who work in this area do, and that is to create a model to be able to estimate. So so this is a Lake Mickey Little River reservoir system. So there are two reservoirs which supply water to the city of Durham, and so what we did was we implemented a hydrologic model which is called PIM, which we have developed in-house. Essentially, it's a finite volume based spatially explicit model with surface, subsurface, weather zone, groundwater, all the systems integrated in one system. So using that, we were able to do the predictions at all the input points in the reservoir. So that's where the reservoir are. So these are all the inlet points to the reservoir. So we will able to predict at all of these, and then we did a quick evaluation of whether we are able to get the stream flows correctly or not, and as well as the water storage in the reservoir. So this is observed and predicted, and we notice good enough R-square and natural cliff, and so we felt confident about it. And then using this tool, then we asked the question, well, what if hurricanes did not happen? Okay, what will happen to the reservoir and its operations? So here what we are doing is a simple experiment. You have a forcing, and then this is, let's say, an Hurricane Noel, and this was in 2007. That's when the southeastern US was undergoing a big drought. And so when Hurricane Noel hit, let's say in North Carolina, so what we did was we ran the simulations with all the forcings, and then we took out Hurricane Noel from it. And if we do it, here is the storage ratio in the reservoir. And now you can see the storage actually goes to zero. In fact, the operating volume of this reservoir is 25%, which means that once the volume gets lower than 25%, they have to they relay all kinds of conservation measures for the city. And so what this tells us that if that hurricane would not have happened, then actually the number of days the reservoir level would have been below the working volume would have increased from 93 to 141 days. And we did this for 33 years of simulations with 24 different hurricane events, and found out that almost 156% increase in the duration of the period when the reservoir will get to below the working volume. So this shows an interesting example of how or why hurricanes are sometimes important for water, not only for ecosystem flushing or riverine flushing, but also for water supply. And this is mostly relevant for humid systems where the reservoirs are much smaller than in western US. The last example I will talk about is how there are instances when extremes can trigger human behavior in a very short period of time, resulting in changes in the hydrologic property of the setting itself. And predicting human behavior is very difficult. I mean, otherwise we would be in the stock market, not here right now, right? But let's say, but that's what I want to highlight, that sometimes this is something we will have to incorporate in our hydrologic systems. So let me dive in to highlight this point. So this example is of Prairie Pothole region. It's in the Midwestern US. So the region extends from southern Alberta or southern Canada and almost to Iowa. So this shaded area is the Prairie Pothole region with an area of around 800,000 square kilometers. And many studies have shown that at least in parts of this, around 90% of the wetlands have been lost. So the region is peppered with these potholes or wetlands because of the deglaciation that happened between around 12,000 to 15,000 years back around in the Pleistocene. Anyhow, so many people have already studied why these wetlands were lost, at least in the recent period, and the study is focused on prairie pothole region of North Dakota. So one hypothesis has been that wetlands were lost because of extended dry periods, and the idea is that if the system got dry, then the wetlands were not wet anymore. So that could be the reason. The second hypothesis is that, well, because of the expansion of agriculture, that led to loss of wetlands. So agriculture essentially encroached upon wetlands, and then people drained the wetlands. And third is wetlands were lost due to drainage expansion, could be related to agriculture or not. Okay. So what we did was, now in these studies, oftentimes what people had done was they looked at historical data, let's say 1980s sometimes, what was the extent of the wetlands then, and then what is the extent of the wetlands now, and they looked at how much is the loss of wetlands. They also looked at the change in the land cover, and they found out, okay, the crop area, at least the row crop, have increased and the wetlands have reduced, so that must be the reason. But when we look at when these wetlands were lost, so we try to track when the wetlands were lost. So at least in North Dakota, we found out that 97% of the wetlands were lost just during this 5-year period from 1995 to 2000. Very weird result, I should say, which forced me to ask my student to check it and check it back again, because it was unbelievable that how the wetlands were lost just in this 5-year period. But Chris was originally from North Dakota, and so he went and talked with a lot of people, and they kind of agreed on it, that that's what must have happened. So let's look at our hypothesis. Well, between 1995 to 2000, actually it is a wet period. If we look at the PDSI, the blue region is the wet period, the red region is the dry period. So the first hypothesis does not work, that was because of the dryness that may have led to. Also, the climate is almost similar in North Dakota, but we see that there is a significant degree of spatial heterogeneity if we look at where the loss was higher or not. So the darker areas are where the loss fraction was much higher. Now we looked at the second hypothesis, which is the expansion of agriculture, but if you look at it, the agriculture has not expanded in this state, so to say. So the land for agriculture has not expanded, but indeed the corn and soybean has expanded significantly after 1995. Okay, so then the possibility is because of the economics associated with growing corn and biofuels and such, and soybean, maybe that's what made it or encouraged farmers. But interestingly, this has continued over time, but most of the loss only occurred during 1995 to 2000. So what could have been the reason? So the working hypothesis was that, well, between 1995 to 2000, it was a wet period. So the farmers felt that, well, continuously last 3, 4, 5 years are wet, and they were, well, we cannot, our fields are flooded. So they were experiencing losses. So as a result of which, they started draining many of those wetlands. And once they started draining, what happened is, once the system reverted or went back to its original state, now these wetlands have been drained, they have been connected. So as a result of which, let's say some of the wetlands become much larger and other wetlands have been drained. Now there are actually data of license that is given for drainage, and we found out that at the time we did this study, there were only 2,600 licenses issued for drainage in the last 20 years or so. And Chris said that there are more drainage just in his ranch or people he knew. So certainly it was not working. Okay, so what we did was we came up with a different alternative way. We looked at an index called shape index, which is root A over P. root of area over perimeter of a wetland. What it does essentially is it does not changes if with different years as the wetness changes, because you can think of it, if the wetland was a cone, just to make it simple, if we do root area over perimeter, area is pi r square, perimeter is 2 pi r, root pi r square over 2 pi r, that's a constant value. So even when the wetness changes of that cone, this does not changes as much, but when there is drainage, as a result of which what will happen is this root area over perimeter relation changes. So Chris did some Bayesian change point detection, found out when this maximum change occurs, and lo and behold, it was around the same time period when the root area of the over perimeter has changed. And so this hypothesis was tested between different counties. So counties where there was significant expansion of the row crop, that's where the change was much more. In the counties where the expansion was less, the change was not there anymore, which suggests that what happened there is the region was wet, farmers thought that this is how it will be, and they will be experiencing losses they'll be experiencing losses, so they decided maybe now it's worthwhile to drain the wetlands, even though that needs some investment. And since they did that, because of that led to reduction. And in fact, in 2000 there was a big flood in North Dakota around Devil's Lake, and a lot of or hypothesis is, or a lot of studies have explored that because of the consolidation of the wetlands, because the smaller wetlands have been drained and all the water is now going to these bigger wetlands and lakes, that has increased the level in those lakes and led to flooding. Long story short, what I want to highlight here is that the wetlands in the North Dakota, they were lost because of the farmers' response to the extended wet period. And since these wetlands have direct implications on flood, that behavior has to be accounted for in our hydrologic predictions. So the take-home point of this short talk is that if we want to have better hydrologic predictions, it is important for us not only to improve our model of hydrologic processes, but also of our dynamic watershed properties. The watershed properties can change because of like forest alterations, the one example that I gave you, because of mortality or because of socio-hydrologic feedback. So those kind of models have to be developed as well if we want to have a robust hydrologic predictions. Okay, thank you.
If you need to leave, I know we're just about one. Feel free to do that, but I'm happy if you want to take any questions.
Yeah.
I don't think I must.
Yes, Prabhakar.
Can you go to slide 7?
Mm-hmm. Let's see. Yes.
So that's a very interesting slide. So let's go back to your Mike Tyson analogy.
Uh-huh.
So there are several ways to figure this reverse thinking point. One is I can bring Mike Tyson and punch you, or I can take all the little Mike Tyson and punch you. Right? So I'm wondering how this thinking point, the median reverse well-trained would respond to scenario. One could be a major drought, other could be some pest infection, which is slowly spreading and creating this.
Right. I mean, generally, what happens is the trees have to be stressed and they have to die, so they have to be stressed and they become susceptible to pests then. So let's say if they are stressed because of the drought, what happens then is let's say some hydraulic failure will happen or carbon starvation has happened, so they are not able to make as much biomass as possible, so they are not able to recover. They are not able to create those raisins which protect them against lot of pests. And when that happens, then that's when, depending on whether there is presence of pest or not, that ends up determining the mortality. So in definitely, if it was, let's say, a forest fire, just a forest fire, many times the systems are so resilient they can recover back. But if there are if there are a lot of trees in a forest which are stressed and they are not able to recover back, in that case what will happen is it will move to an alternative stable state. And by that all I mean is, let's say if you were in pine forest and if you hardwood forest, I'll give an example, and if there was forest fire in there, then the light regime on the forest floor will change suddenly because now the canopy is not there. And so some other plants which grow much faster than hardwood trees like pines, when the light is sufficient, they will start growing. So as a result of which tree succession will start and the forest structure will change significantly. But in certain circumstances what can also happen is that the trees may not grow because suddenly the density has become so small that the number of seeds they produce, and if you calculate the probabilistic fecundity of how many offsprings will be born from n number of trees or n number of seeds that are produced, that will not be sufficient and other competing species will take over, and these could be even grasslands. But long story short, it can be small stress, small persistent stress that can get us here. Right.